I'm up. All right. Hey, welcome back. Bright and early, 8:30 a.m., nice and cold outside. That's great because I grew up in Indiana and it's supposed to be cold in January. This is not cold enough. Okay. What I want to do today is finish this broad brush overview and a reminder that you don't need to follow every last point and jot and tittle as we go through. And then I'll go back for the course of the semester, of course, and flesh in all the details and go deeper. So we left off looking at this sparse lower triangular solve. All right. Now, so the idea is that if B4 is non-zero, then X4 is non-zero. If X4 is non-zero, you've got to subtract that X4. You've got to multiply that X4 times whatever this red value is here, and subtract it from the right-hand side for the ninth position. So because of this non-zero, and if X4 is non-zero, then that causes X9 to become non-zero. So there's two things here that happen. There's a numerical dependency. I have to have computed X4 before I can use it to update X9. And X9 will become non-zero as a result, and will stay that way. And remember, whenever I say non-zero, I'm going to not make this caveat any longer that 3 minus 3 is non-zero. Now, these subtractions from potentially X4, X2, and X6, of course, can be done in any order, because addition and subtraction are associative, commutative, all that jazz. X2, though, is equal to 0. So if I would be taking X2, which is 0, hard 0, multiplying it by this value, and then subtracting it from X4 or X9 or 7. But see, that we don't have to do that. We can skip that work. We don't have to. Hopefully, that we don't even have to test whether X2 is actually 0. Just skip it altogether. So the important thing, there's two important things about this. One is this numerical dependency gives you the order in which this computation has to be performed. You've got to do this, compute X4 before you can use it to update X9. And so one order of doing this would be, okay, do the step 4 and do step 6 and then 9, 10, 11, 12, 13, and 14. That's one way of doing it. But I could, in fact, do it in any topological order, any order of these nodes which respects those arrows. Okay? And that's what this list down here is. 6, 10, 11, 4, 9, 12, 13, and 14 was what we found from a first depth first search from node 4. And then a second depth first search could be prepended onto that. 6, 10, 11 gives us those nodes. So that's the dependency. And this right here is a valid order in which to do the computation. That's important because if I wanted to sort this, it would take more time to sort than it takes to use. I can produce this list in linear time, linear in the size of the list. But to sort it would add an extra logarithmic factor, which is potentially more than the work involved. So there's the dependency, and then what we do then to determine the non-zero pattern is put your fingers on 4 and 6 and do a depth first search of the graph from these two starting nodes and see what you can see. And the red nodes are all the nodes you can reach from B4 and B6, which are the non-zero positions in the right-hand side B. So there's a depth first search involved, and the beauty of this is that a depth first search produces naturally a topological order. So if you look at all these nodes from 6 to 14, if you consider all the edges in the graph mapped down to this list, they all go from left to right. That's what's meant by topological order. And the other thing that's important about this depth first search that I'll show in a moment is that the time it takes to compute this depth first search is proportional to the number of edges traversed. You're not going to necessarily traverse all the edges of the graph. What edges are you going to traverse? The edges you traverse will be, for example, this edge and this edge and this edge. But you see, this edge contributes then 1 to the depth first search time. That's a purely symbolic computation to find this non-zero pattern. But it also contributes it corresponds precisely to exactly 2 floating point operations, taking X9, multiplying it by this number, and subtracting it from X12. That means that the time it takes to do the depth first search to find this list is proportional to the flop count in the next step, which is the numerical step. So now what I can do, instead of this, which is bad, It's n plus n flops. I need the non-zero pattern to get at order flop time. I can do this instead. I compute the reach of the B nodes in B in the graph of L, and then for each j in X in topological order, do this work. And the reach is very simple. It's just a depth first search. You start with every node in B. If it's unmarked, you do a depth first search, and then it's just a standard DFS. So the total time now is order flops, because every edge you visit corresponds to 2 flops you'd have to do here. So it's perfectly balanced. And the order n time is gone. So now the reason this is important, well, it's two reasons. One reason it's important is it's a useful problem in its own right. Solve a sparse linear system, it's lower triangular. That comes out if you factor a matrix, you want to solve a linear system, you've got to do a upper-lower triangular solve. But the other part it's useful is that you can use this triangular solve as a kernel inside a bigger algorithm, namely LU factorization. So in LU factorization, which I'll derive numerically as we get into the course, so it's been a while since you've seen LU factorization, don't worry, I'll show you how it works as long as you understand matrix multiply, and I'll even refresh that. This is going to be a left-looking step. It's going to compute at the kth step of factorization. This is the frontier that I'm not modifying nor computing. So it's go east, young man. It's moving from west to east. It's going the wrong direction. Anyway, but it's going from left to right. And at this point here, to compute the red column, we're going to look left and pull in values of L, and actually not values of U. I could have left this white. This is just a right-only data structure. This is a right-only object here, U is. And this is the algorithm, and I'll derive this later, but basically you start with an identity matrix. You do a triangular solve with the right-hand side being the column of A. And this vector X gives you two things. It gives you the column of U and it gives you the column of L when you divide by the pivot. You can also do partial pivoting with this. I'll explain that as we go into the course. So these two steps here, just dividing a sparse, copying a sparse vector, dividing a sparse vector, all those can be easily done in time proportional to the size of those vectors. So that's not a problem. The core of this algorithm is this. Now, here's the deadly n squared if you do it wrong. If you take order n time to do this, you've got an n loop out here. The total time is n squared, which is pathetic. If I have an n by n tridiagonal matrix, I should be able to factor it in order n time. But if I did order n in this step, the whole algorithm would be n squared, and you would just throw this out as a piece of trash. So it's vital that this be done in order flops. If this is done in order flops, then the entire thing is done in not quite order flops, because there's still now an order n loop. The total work will be, I don't have it here, but the total work would be, of this algorithm would be n plus flops. But if we assume, let's see, if we make some very simple assumptions that, for example, if we assume that, what's the assumption we need to make? I know what they are, but I don't want to explain. But under very simple assumptions, the work of this algorithm, the flop count will be larger than n anyway, because if you've got to do these n divisions. So there are cases where you don't have to do those divisions, but that's a minor point. So here's a sparse Cholesky factorization. It can be done using the same kernel. So this is an example of a block matrix expression, and I'll explain what this means. But basically what I've done is I've taken this matrix and I've sliced it. This is an n by n matrix, and I've sliced it into n minus 1 rows and columns, and then the last row and column. And the same thing here and the same thing here. And when you do that, you can now pretend that these objects here are, if you will, just individual scalars, if you be careful about the order of multiplication. And you could just, okay, if these were 2 by 2 matrices, we do L11 times L11 transpose equals A11. And so this gives us a recursive algorithm. If we first factorize the leading n minus 1 by n minus 1 part of A, okay, that's, if you will, recursive, then we have another piece. We've got L11 times L12 equals A12. That's a triangular solve now. I have this times this equals this. I'm not needing to do a matrix vector multiply, this being the matrix, this being the vector. That's my unknown, L12. I have a matrix that I know, because I've computed it here, a vector I do not know, and a right-hand side that I know. That's a sparse triangular solve. We just saw how to do that. And then this piece right here, this times this equals this, gives this equation. L12 transpose times L12 plus L22 squared equals A22. And I can solve that for L22. So there's sparse Cholesky factorization. This is a recursive step, so that's easy. That's done. This is the sparse triangular solve. We now know how to do that. And this is a sparse dot product, which is of a vector with itself, which is easy to do because you're taking a vector, transposing it times itself. So you're basically taking each of the entries in those vectors, squaring them. So if you have the non-zero pattern, you just walk over those values and you're done. So that's easy. And then take the square root, and we're done. And so, so there's the algorithm. Unrolled. The recursion now is unrolled. You just do a triangular solve and do a dot product. This gives it what's called an uplooking algorithm, because now what we're doing is we're accessing this part of the L matrix in order to compute the kth row of the matrix using the kth column of A. And I've only drawn the one column of A, not all of it. With sparse Cholesky factorization, there's a very important combinatorial structure that guides our work called the elimination tree. And what the elimination tree is, basically, it's if you will, a spanning tree or a tree that's a subset of this graph back here. Okay. And what it's going to be is, for any given node, we're going to have one edge going out of it, only one outgoing edge. And that's the lowest numbered node. So we throw the edge away from 6 to 10 and only keep 6 to 9. Okay, so we end up with a tree. And so the tree is given by the first off-diagonal non-zero. Now here, this actually, there's no tree for this L matrix because the tree only exists for the Cholesky case, and this is a more general matrix. So I won't, so let me go back. Whoops, wrong direction. So this elimination tree can allow us to compute the non-zero pattern not in the flop count time, but in time, remember that's calligraphic X that I needed to compute in the general case in order flop time. Well, ideally, if I could compute it in order of the size of the output, that would be optimal. Well, the elimination tree allows us to do this because of the special structure of the L matrix for Cholesky factorization. And the idea comes from a pruning of that graph. And I'll show you why we can prune that graph. So consider, but we can't do this in the general case. We can do it only for the L that comes out of Cholesky factorization, where with Cholesky of L times L transpose equals A. A is a symmetric matrix. You have to have that for this to work. So let's think of what happens when we can compute the kth row here of the L matrix. Okay. Let's suppose, remember that picture we had in those rules. Because this solution to this lower triangular system will become the kth row of L, then this entry here in the solution to that system is identical to this value here. And so there's a rule that says, well, LKI is non-zero if and only if XI is non-zero for this triangular solve at the kth step. Okay. Then, if Xi is non-zero and there's an LJI that's non-zero, where J is less than K, then Xj will be equal to non-zero. Okay, that's the rule we had before. But this Xj, because this, again, this solution will become the kth row of L when I'm done, because the triangular solve I'm doing at the moment is through K minus 1. So I'm constructing this kth row. But I want to ask, what's this kth row look like, and how can I then prune this graph accordingly for subsequent solves? If xj is non-zero, then lkj is non-zero. So now I've got two rules. Essentially now, lki is redundant for computing the reach of the graph for subsequent triangular solves. Because I've got basically, because I've got this non-zero and that non-zero together, they imply that this value will be non-zero. So now that, since I know that this entry here implies this will be non-zero, the question is if I'm at node I for subsequent triangular solves for computing rows of k below here, I don't need this edge. I don't need the edge lki to compute the reach of the graph. I can get here in 2 steps rather than just 1. Now you might say, well, gee, why not keep the shortcut? Isn't that better? No, because when I do this pruning, I end up with a tree, and that's better still. I don't have to do a depth first search of a whole graph. I can do a DFS of a tree, which is much simpler. So the presence of this edge and this edge implies the presence of this edge. What that means is I can throw this first edge away when I compute the reach. And I would still have the same result if I prune that edge in finding the reach of the nodes in B. So if I prune lki, this edge from k to I, what that means is then any edge below, suppose j is, any non-zero below the first entry can be thrown away. Like if there was another entry above this, well, I could throw j away as well. So I can throw anything below the first off-diagonal non-zero in the kth column. And what that leaves me with then is a tree, because every node has just now a single, node I now only has a single outgoing edge to a node which is higher in number. So there's no cycles in this graph. There's no cycles in the original graph L because all the edges go from low-numbered nodes to high-numbered nodes. So there's no cycles to begin with. And now that there's no cycles, there's also only a single outgoing edge for every node, so that's a tree. So the parent of a node in the tree, the parent of node I is j, where j is the smallest row index j larger than I, such that lji is not equal to 0. All the other edges in this graph are redundant for computing the reach. And once I have this elimination tree, I can compute the reach in linear time. So if you have a tree, and it's not going to be a binary tree, and it's in fact going to tend to be very very thin at the top and very bushy at the bottom. If I want to compute the reach of the nodes, a reach of a set of nodes, suppose these nodes are non-zero in B, the right-hand side, B being a column of A. And I want to compute the reach. Where can I get to starting with these nodes? All the edges go upward. Okay? All I have to do is walk this path. And that takes time proportional to the length of the path. Mark the nodes as you go, and then start here. And stop when you see a marked node. Start here and stop, start here and stop, start here and stop. And so what I've done is I have found the reach of this graph in time proportional to the number of nodes I can reach. The reach of these nodes, which gives me the non-zero pattern of the kth row of L, because the kth row of L comes from that triangular solve. So here's an example of a matrix A, its Cholesky factor, and its elimination tree. You see that, for example, 1, the parent of 1 is 6, the parent of 2 is 3, the parent of 5 is 8, and so forth. So this tree then governs our factorization. And if I wanted to find, let's say I wanted to find the non-zero pattern of, let me pick an interesting one. which is an interesting one. There's not a lot of fill-in in this graph, so it's kind of boring. Let's suppose I wanted to compute the non-zero pattern of row 9. Okay? Then what I would start with is this column of A, which only has one non-zero in position 6. And I walk up the graph towards 9, and I'm going to stop at 9 because as I'm building it, the graph is no bigger. It would be no bigger than that. And so from 6, I see 7 and then 9. But see, that's the non-zero pattern, 6 and 7. So there's the reach right there. There's that picture right here that I drew applied to computing row 9. So then the symbolic analysis of Cholesky factorization starts with a fill-reducing ordering. That's an entire chapter in the book. We'll spend a lot of time there. You don't want to factor the original matrix. You want to permute it to get low fill-in. This is an NP-hard problem. So we have to use heuristics. Finding the elimination tree can actually be done quite efficiently in time, nearly proportional to the number of non-zeros in A. I use this magnitude symbol on matrices to mean the number of entries in the matrix, the number of non-zeros in the matrix. Then I need to do a depth-first post-ordering of the elimination tree, which is linear time. And then I need to compute how many non-zeros there are in every column of L. That's also nearly linear time in A. And then some methods find the actual pattern of L. And then numeric factorization, there's lots of ways of doing it. There's the up-looking method that relies on lots of triangular solves. There's a left-looking Cholesky method, which is supernodal, which what that does is it lumps together columns of similar non-zero pattern, and when it or identical non-zero pattern. And when it does that, it can use dense matrix techniques within that supernode to exploit cache efficiently and get very high performance. There's also a similar thing called multifrontal, which I'll highlight as well when I look at LU factorization. So left-looking Cholesky is a little bit different than up-looking Cholesky. In left-looking Cholesky, at the kth step, we're computing this kth column, and we're looking left to use this part. So this is different than the up-looking algorithm. And here's the computation. But to do this computation, I still need this notion of the tree. I still need this notion of the reach of a graph. The reason being is that when I want to compute this, I need to take this row of L and multiply it by this matrix. But of course, you only have to do this for the non-zeros in that row. And then add it into the kth column of L. And so the question is, what is this non-zero pattern? Well, that's just the reach. Again, because even though we're not doing a numeric triangular solve, that solve is what's governing the non-zero pattern of this kth row, and the pattern is then governed by the reach of this tree. So if I have the tree and I have the non-zeros in the kth row, I can easily find the non-zero pattern of the kth row of L. And then I can go and use those columns and add them. And then I've got to do a square root and then a division. Now, in a supernodal method, we can lump together columns with this identical non-zero pattern. The tree will look like this because the parent of 4 would be 5. The parent of 5 would be 6. And if I can detect that the non-zero pattern of these 3 columns are all the same, then I can lump them together. And this happens a lot in matrices because of the way they fill in. And it's from a chain in this elimination tree. And what can happen is we can exploit dense matrix operations. I don't have to use irregular data structures for this. I can pack this in a little bitty 1, 2, 3, 4, 5, a 6x3 dense matrix. So I take these values, pack them in a 6x3 dense matrix, and do a little Cholesky factorization on those. So now we're working on blocks of the matrix. So the block method is called the supernodal method. It's block left looking. It's left looking because, again, we look to the left to compute the kth column And all this picture looks the same, except this dot is no longer a scalar. It's a submatrix. It's a dense submatrix. So we have a matrix multiplication here. Instead of multiplying a scalar times a vector to add to a vector, I take a matrix times a matrix and add it to a matrix. And that's powerful because multiplying two matrices together and adding them to another matrix, okay, is what CPUs are designed to do efficiently. I mean, if you play a first-person shooter game and all these polygons are flying at you trying to kill you, right, well, there's a translation, rotation, scaling, and so forth that has to happen to move those polygons to the right place. Those are lots and lots of little bitty 4x4 or 3x3 or 4x4. I think it's 4x4 matrix multiplies. So your GPU hardware, for example, or your CPU, is well tuned, well crafted to do this very efficiently. And same thing with scientific computing. Scientific computing relies heavily on multiplying two dense matrices together, and that operation works very well on a system with cache. Let me take an aside and explain why that is. Suppose we have two matrices that fit in cache. And if we don't, we can chop the matrix up into pieces. Each piece fits in cache. So I have a matrix here that's of size n by n, a matrix A, and I have a matrix B of size n by n. I can load them into cache. Okay, and so the memory traffic here is order n squared. Roughly 2n squared words have to be brought in. Okay, and if I'm doing, say, c equals a times b. Once they're in cache, I've got n cubed operations to do, n cubed floating point operations to do. And then I write the result back, say, out of cache, and so I have a total of 3n squared data transfer to and from cache with n cubed floating point operations. So the ratio of floating point operations per memory access is n cubed over roughly 3n squared, or however you want to count it. It's basically n. It's 1/3 n. Okay. So what this means is that your CPU here that's doing these flops can be n times faster than your memory transfer, where n is the size of your matrix, and your cache just has to be big enough to fit these n squared blocks in it. So, for example, n is, say, 32 is a common number. If n is 32, your cache size is on the order of 1,000. 32 by times 32 is 1,000. It's just a few thousand words. That's not so bad. Each word would be 8 bytes for double precision arithmetic. So it's a modest size cache to handle this. But this ratio is about n. So your CPU can be roughly 32 times faster than the memory traffic, and you've got a balanced system. Memory is just able to keep up with the CPU. They're of the same speed, the same amount of work that they have to do. And that ratio is about what CPUs these days have. The CPU is 10 to 20 times faster than the memory bus. But cache, this block matrix multiply can operate at the CPU speed because the memory traffic is low compared to the amount of floating point operations that are happening. If, on the other hand, we just bring in a scalar, work on it, and spit it back out again, and our computation is irregular, then that value does not get cached and reused efficiently. So for every memory reference I make, I do a couple or one or two floating point operations, and I put it back, and I don't use cache. Now I'm running at the memory bus speed. So I'm running 10 or 20 times slower than what I could be. So that's why algorithms like this work 10 or 20 times slower than faster than the algorithm I just showed you earlier that does not use supernodes. So anyway, once those dense matrix multiplications are done, there's in the scalar case, we have to take the square root. Well, the square root of a matrix is the Cholesky factorization. So I have to do a dense Cholesky factorization. Then I've got to divide this column, well, it's now a matrix, by the diagonal, and that turns out to be a dense triangular solve. So that's supernodal method, and that's what's actually in Matlab when you do a Cholesky factor. When you do a backslash with a symmetric matrix in Matlab, this is what it uses. Multifrontal method is a different approach. In some ways, it's a little easier to understand if you can just picture what Gaussian elimination would look like on a sparse matrix. It has the same tree. I've got a symmetric graph here. And let's just look at, there's lots of ways of factoring this system. But now let's just pretend we're using standard old Gaussian elimination. Vanilla. Okay, so what happens with Gaussian elimination? Well, with Gaussian elimination, it's a right-looking method, because what happens is you compute the first row and the first column of the L and U matrix. Now this is LU. And then you want to take this row and this column, and you want to multiply the two together and modify the resulting matrix. Right? So you take, in other words, you're taking, what do you do with when you're doing Gaussian elimination? You take the first row and the first column, multiply them together, and use it to modify this matrix. Okay. Now, in the sparse case, what if only, say, 3 of those entries are non-zero? And since it's symmetric, those same 3 will be non-zero here. So I'm going to take this row vector, multiply it by this column vector, and I'm going to touch this matrix. What will I touch? Suppose this is 5, 10, and 12. 5, 10, and 12. In other words, row 5, row 10, row 12. What will happen, and this is 1, what will happen is I will exactly touch these entries. That's a dense submatrix. If I now take this and throw away everything else except for 1, 5, 10, and 12, I can represent that computation in a little 4x4 dense matrix, where if all I'm interested in doing is computing these updates, I can put them all here. So that's what I've pictured here. Now those updates, I could do one of two things with them. I could sort of put them back into the big matrix, because these values have to be added here. Well, that's one way of doing it, but that's horrible. Okay. What I want to do instead is, well, when do I need these updates? I don't need them. Like to do step 2, I don't need them. Because to do the Gaussian elimination for step 2, because that's 0 here, step 1 doesn't affect step 2. And these updates do not depend on what was here. These are updates to whatever it will be there. But the actual value of the update only depends on this row and this column. So step 2 can be done independently. There's parallelism here. But there's also this idea that, well, I only need these updates when I get to step 5. And what happens when I get to step 5 is I need all of them, or at least I just need these. What this means is, if you hear, for example, and these numbers aren't the same as the ones over there. I probably should have picked the same numbers. But if I go, say, from here to here, because I ignore numerical cancellation, these values will be non-zero in the 5th row. And so all of these 9 updates, all of these 9 terms, can fit in the frontal matrix of the fifth frontal matrix, which is simply, well, here from 1 to 6, this is the parent. It's the very first off-diagonal non-zero from 1 to 5 tells me, oh, who needs these values? 5 does. 5 is my parent in the elimination tree, which is just described on the previous slide. So this is like, this picture here is the elimination tree where every node is blown up to show you what happens inside each frontal matrix. So the work is like this. You do one little bitty mini step of Gaussian elimination here. You don't toss these results back to this matrix. You leave them here. You feed them to your parent. So all these 4 values need to go to the parent. And you notice where they fit, 6 and 7, And this is symmetric, so it's 1, 6, and 7. These 4 values fit right here. And these 4 values fit, they sort of spread apart. These 4 values fit here. And these 9 values all fit here, and so forth. These values here, 8 and 11, fit here. Everybody fits into their parent. The parent is a superset of all its children because of the way the fill-in happens. And so a multifrontal strategy does little bitty dense matrix factorizations, little bitty steps of Gaussian elimination. Here, though, this is different because it says that, well, hey, nodes 7 and 9 have the same non-zero pattern. Why would I have one frontal matrix with this 9 by 9 block and then have another one that's 3 by 3 that do the step for doing step 9? Step 9 is a superset of its child minus node 7, but it's actually equal. It's not just a superset; it's actually equal. 7, the pattern, in other words, the pattern of 7 minus 7 itself is always going to be a subset of its parent. See this here, for instance, 6. If I take out 6 itself, 7, 9, and 10, this list, this set, is a subset of this set. Okay, but in some cases, here, for instance, if I take this off, I have 9, 10, 11. Well, the frontal matrix for 9, 10, 11 will not just be a subset, it'll be equal. So these two fronts can be laid on top of each other, and I can do 2 steps at the same time. And so you can do 2 steps of Gaussian elimination inside this matrix. And that's powerful. Okay, for the same reason that this is powerful over here, the matrix-matrix multiplication, where I multiplied 2 n squared, yeah, there we go, thank you. I'm watching the monitor on the back, so it's like, point to this slide, panel. Okay, in this matrix-matrix multiplication, we had a size n data object that was dense that fits in cache. Okay? Well, the same thing happens with dense matrix factorization, a Gaussian elimination. What each kernel says then, I have to take an n by n matrix, where n is going to be small. It's going to be however big my frontal matrix is. And I need to do some steps of Gaussian elimination, and then I'm going to stop. Well, if I have to do k steps, then the work here is n squared times k. But the memory traffic is only n squared. So I have a factor of k advantage. Okay? Think of this. So you've got a CPU and a memory. The CPU says, okay, give me n squared pieces of data. I'm going to chew on this now and do n squared k work. I've got k times more work to do than I have data to pump through the memory bus. And if k is big enough, then both the memory bus and the CPU are kept running at full throttle. Okay. As a result of this is what happens when you do backslash in Matlab for an unsymmetric matrix. And this algorithm and the supernodal algorithm can operate at somewhere, let's see, I'm trying to remember the exact numbers. They can operate close to 80% of, no, let's make it 50%. 50% of the theoretical peak performance of the machine, which is multiple gigaflops usually on a modern CPU. And that doesn't, it's like, well, of course you should be able to get that. Well, no, that's very difficult. Because it's a very irregular computation. When you have an irregular computation, you don't work at the speed of the CPU. You work at the speed of the memory bus, and that is dog slow. Oh, that's another idiom. Right? You know what that means, right? No, it's not used too often. Yeah, I've heard it. You've heard it, yeah. I use it from Indiana. We must use it more there. I don't know. Not even all Americans know what that means. Anyway, something that's very slow. All right. Dogs are not, I can't quite figure out the source of that idiom because I've got a little Sheltie and man, is he fast. He's not slow at all. So I don't know any slow dogs. Okay. So both of these methods are able to exploit locality. And there are three main things that affect the performance of an algorithm, whether it's sequential or parallel. Locality, locality, locality. You've heard there's three things that affect the real estate value of a house. Locality, locality, locality. Location, location, location. It's the same thing in computer science. You can do this with an unsymmetric case, and I'll skip over this quickly here. Now the frontal matrices become rectangular. If for example, over here in this picture, if the pattern is unsymmetric, if this pattern 5, 10, and 12 isn't the same as this, suppose this is something altogether different, 7 and 8. Okay, now you get rectangular frontal matrices. That's all that's different. Instead of square, they're rectangular. And now, however, because they're rectangular, not because they're rectangular, but because they're unsymmetric, the parent is no longer a subset of the child. And sometimes these entries can go to the parent, sometimes they have to go up to the ancestor. So now backslash in Matlab. Now you've seen all these different methods, which we'll go into depth in great detail in the book as we go through the course of the semester. So you've seen, again, this very broad brush overview of the entire course. So don't panic, as I said, if there's something you don't understand. I expect that. All right. If you understand everything I just said, then you should leave. Okay, because you're done. So backslash in Matlab, when A is sparse, it's a meta-algorithm. It looks at the matrix and says, oh, I know what method I should use, and uses the right method. And sometimes it tries one method and then goes and, oops, that didn't work, I'll try another one. It's a fascinating meta-algorithm because Matlab, it doesn't know at the beginning, well, it's a black box. Okay, so it's very easy to check if A is diagonal. If so, just do scaling. That happens very frequently. Scale each row. If A is a banded matrix, so it's stored in a sparse format. We have lists of columns and their row indices. Okay. The meta-algorithm at the top level can look at this sparse pattern and say, hey, all of these rows fit within a nearby band on the diagonals. In other words, it looks like this, where the values, this is all 0, and the values in here are more than about 50% non-zero. And if it finds that, it converts it into a band matrix data storage, which if the bandwidth is the size k for an n by n matrix, it basically stores it in an n by k dense matrix. It sort of takes it and flips it, and then it uses a band solver. Otherwise, if it's upper or lower triangular, it uses a forward or back solve. Otherwise, if it's rectangular, it uses, oh, this is wrong. I fixed this. This was the old code. I now have a multifrontal sparse QR. This is a non-multifrontal code. I replaced this in Matlab a couple of years ago. If it's symmetric and all the diagonal entries are positive and real, it tries Cholesky, which is using my code, Cholmod, which is this sparse Cholesky factorization. And within that, there's even two different methods. Within Cholmod, mod stands for modification. It can do more things than just Cholesky factorization. There's a chapter in your book called Update and Downdate. You have the idea there with an update downdate is you have a Cholesky factorization of a matrix. Okay, great. A equals LL transpose. And then you say, oh, I should have had a V8. That's a joke from an old advertisement. Oh, I should have factored a different matrix. Well, your matrix changes a little bit. Just a little bit. It has a low rank change. Well, you could start from scratch, and you now know what that idiom means, and factor the matrix from scratch. Or you could take your existing factors and patch them up. And it turns out that that's much faster than computing it from scratch. And that's the update downdate. That's where the mod comes in Cholmod. Matlab, though, doesn't use that part. But I do also, inside this package, need to do a Cholesky factorization. But what happens in this symbolic analysis, now I've shown you two different Cholesky factorization methods. An uplooking, which doesn't use cache, doesn't exploit cache. But it's very simple, very elegant. It fits in the book. That's a 6-minute warning? 5-minute. Okay, thank you. or a supernodal method. But the symbolic analysis of those two methods are the same. So I can do the symbolic analysis, and I can look, and I can say, well, is this flops per memory reference ratio? This is the flops for the entire algorithm, and the memory would be the total memory usage of the algorithm. If this ratio is larger than about 40, then that means let's exploit dense matrices. Let's use a supernodal method. But if this ratio is small, then trying to exploit supernodes is not going to buy us much. And in fact, it'll cost us because there's all this overhead of moving data around in these really bizarre, funky data structures, and it's just a little more complicated. It's not asymptotically slower, but it's just more work in a constant sense. And so if this ratio is small, well, just use the simple method that's in the book there, and it'll be faster by about a factor of 2 for extremely sparse matrices. So this right here is itself a meta-algorithm. So you've already got a meta-algorithm on top, and then it decides, oh, okay, pick the right Cholesky factorization. But this might not work, because you don't know if the matrix is symmetric, positive, definite. All you know is that the matrix is symmetric, and it has a zero-free diagonal. That is a necessary but not sufficient condition for it to be symmetric, positive, definite. If the matrix is symmetric, positive, definite, then it will be symmetric, and it will have a positive real diagonal, but not the other way around. But determining if it's symmetric, positive, definite is very difficult. Pretty much the answer is, well, you do a Cholesky factorization. If all the diagonals are positive as you factor it, then it's positive, definite. Okay, well, that means we actually have to do the work. So we'll try it. We'll try Cholesky. If it works, great. If it fails, or if these initial tests, like if this test fails, or if you try Cholesky and it fails, then use LU. Depending on, it's either using a multifrontal or a left-looking. And you can see these algorithms here if you're interested. So it's a fascinating meta-algorithm. This whole, all these bullet items, okay. There's more to this. There's a few extra little details I haven't added. There's 6 or 7 or 8 different factorization methods used. The total, I asked Penny Anderson at the MathWorks once, my colleague there who has done a lot of work on this. I asked her once, well, how many lines of code is in backslash for the sparse case? She couldn't tell me. Not because it was proprietary, but she couldn't count that high. Okay, this package alone is about 20 or 30,000 lines of code. This is about 50,000 lines of code. This is another 20 or 30,000 lines of code. The LA pack is another 50 or 100. There's probably 250,000 lines of code. I'm not joking. There's 250,000 lines of code here. If you were to print that out, it'd be a stack this high. And the interface to that 250,000 lines of code, it's the simplest interface known to man. It's a single character. Okay. Can you describe an API that's simpler than a single character? No. So this algorithm probably has the highest ratio of lines of code per complexity of the API known to man. Okay. So there's this book. These are old slides, as you can tell, that we're using for the course that describes this. There's other things inside the book. For example, this update downdate. Here's this notion of you have a factorization, you compute it, but now you say, I should have done this instead. Now Wilkinson said this problem is one of the most important algorithms in linear algebra. What's interesting, though, is that it's not actually used that much. Wilkinson was maybe ahead of his time. I don't know. But what's interesting about this, factoring this is expensive, but updating it takes time proportional to the number of entries that change in the matrix. And think about that. You can't get any better. So this is an asymptotically, provably optimal method, which was very difficult to obtain. And it depends on all the theory you've seen before. It depends on that tree. It depends on the depth first search. It depends upon all those different things. And it turns out to be, again, the triangular solve that gives us all that with the DFS of the tree. So this tree, as I said, this triangular solve is sort of like the main character in a plot that sort of ties the whole novel together, all right, is that sparse triangular solve. So if you understand the sparse triangular solve, you'll understand, that's sort of like Oliver and Oliver Twist. It's just this little guy that just goes through the whole book and meets these characters along the way. So anyway, let me wrap up. We've got direct methods for sparse linear system, the backslash. It's sparse matrix algorithms is a beautiful combination of numerics plus graph theory. The goal of this course is sparse methods from the ground up, from scratch. We'll look at the lower triangular solve. We'll look at sparse LU, sparse Cholesky factorization. We'll look briefly at supernodal multifrontal methods. We'll look at the update downdate, and we'll look at a bunch of other methods as well that are in the book that I haven't touched on, and in the book. And at that, I'm at 9:20, so we will stop and pick up here in chapters 1 and 2, 1 being the background and 2 being the meat, start of the meat, on Monday. So thank you.